Why do engineers need so many material properties? Because a material that survives one loading condition may fail under another. We must ask whether load is single, impact, cyclic, or sustained, and whether the time and temperature will change the response. Let us now look at all the properties one by one. Ductility. Ductility is the ability to undergo substantial plastic deformation before fracture. A ductile tensile specimen elongates permanently and usually forms a neck. Engineer measure it using percentage elongation and percentage reduction in the cross-section area. Mild steel, copper, and aluminum are common ductile material, and ductile material can be drawn into wires. What do you think about rubber? Rubber? Rubber creates an important misconception. It can stretch far, but most of that deformation is recoverable and under elastic limit. Ductility specifically describes the permanent plastic deformation before the fracture. Many elastomers rupture with a little permanent plastic deformation, so their fracture can be brittle like. Mild steel is metallurgically more ductile because it yields, plastically elongates, and necks. Next, brittleness. Brittleness means fracture with little or no plastic deformation, often with limited warning. As carbon content increases in iron carbon alloy, hardness and strength gradually increases while the ductility decreases and toughness often falls. The trend explains why mild steel is more formable than high carbon steel, though heat treatment and microstructures also strongly influence the results. Next, resilience. Resilience is the capacity to absorb energy elastically and releases during its unloading. Proof resilience is the maximum total energy a component can store without permanent deformation, and modulus of resilience is the energy per unit volume represented by the area under the elastic part of the stress strain curve. Next is toughness. Toughness is the ability to absorb energy before fracture. Total toughness refers to the total energy absorbed by the complete component, while the modulus of toughness is the energy per unit volume. It equals to the entire area under the engineering stress strain curve up to fracture. A tough material combines both strength and ductility. Next, we have fatigue. Fatigue is a progressive damage caused by the repeated and fluctuating stress. Failure can occur even the maximum stress is well below the yield stress. A fatigue crack first initiate and then grows gradually with each cycle and finally cause a rapid fracture. The stress strain curve relates the stress amplitude to the number of cycles to failure. Next comes the creep. Creep is a time-dependent permanent deformation under sustained load, specifically at higher temperature. Primary creep begins with the decreasing strain rate. Secondary creep has an almost constant minimum rate and often controls the service life. During tertiary creep, internal damages and sectional loss accelerate until rupture. Turbine blades and boiler required careful creep design. Now comes to the important part, material selection. Material selection begins with the loading history. Wire production requires ductility, spring requires more resilience, crash structure requires toughness, rotating shafts require fatigue resistance, while the turbine components requires creep resistance. The strongest material is not automatically the safest choice. Engineers select the property that matches the load, time, temperature, and failure consequences.